Chapter 3, first section is on exponential functions and their graphs. We'll begin with a brief definition here of what an exponential function is up on top here. It looks like f of x equals a to the power of x, where a is going to be a number greater than 0. Basically, it means it's positive. If it was negative, this would become negative, positive, alternating for consecutive x values, and that would not be considered smooth graph behavior. A cannot be 1. If it was, 1 to any power is going to be 1, except for 0. And the exponent can be any real number. So here's an example of two exponential functions. We have f of x equals 2 to the x on the left, and f of x equals 4 to the x on the right. And we want to graph these things and compare their graphs to each other. So what we're going to do here is I've made a table. I'm just going to take these x values and plug them in and evaluate the functions. So I'll start with the ones that are going to be most familiar. X is 1. 2 to the first power is just 2. 2 to the second power is 4. 2 to the 0 power is 1. Any number to the 0 power is 1 except for 0. That would be undefined. Now negatives. When I have 2 to the negative 1, let's recall what 2 to the negative 1 power means. That means 1 over 2 to the positive 1 power, which just becomes simply 1/2. So negative 2 will give us 1/4. So if I plot these points, negative 2 at 1/4, negative 1 at 1/2, 0 at 1, 1 at 2, and 2 is at 4. Actually, here I can add one more. I'll add 3, because 2 to the third power would give me 8, and that's still going to be on the grid here. So right there. So this graph is going to be an asymptote. It's never going to touch this. I'll explain that in a moment. But it will curve up here. Try and draw this as accurate as we can. That's not too good of a drawing, but that'll do. Now, it's never going to reach the x-axis. I know that because, say, for instance, I plug in the value negative 100 for my x. Well, that would be 1 over 2 to the positive 100, which is going to be very, very, very small. Choose even smaller number, negative 1,000. 2 to the negative 1,000 will be 1 over 2 to the positive 1,000, which is really, really small. I'm just going to keep on getting smaller as I go to the left. Now this chart here, similar thing. If I plug in these x values, I'm going to get 4 to the first power, 4 to the second power, 4 to the 0 power, 4 to the negative 1 power, 4 to the negative 2 power. I'll put this one in a different color when I graph it. At negative 2, this one's going to be even smaller. This first graph was 1/4. Well, this one at that point is 1/16. So it's smaller. And at negative 1, it's only going to be 1/4 instead of 1/2. But they share the 0, 1 point. That's going to be common of all our graphs. Now this one, to the right of the y-axis, it grows faster. At 1, instead of being at 2, it's already at 4. And at the x value of 2, it's already off the graph at 16. So even though this one starts out lower than this one, than the green graph, it's closer to the x-axis over here. It'll curve up, and then it will surpass it. And on the right side, this graph is going to grow faster than the other one. So we'll be able to tell two graphs apart. For instance, if this was a matching multiple choice, we could tell that because for positive x values, the blue graph is growing faster. That means that this number has to be a bigger number. I want to point out real quick here something about fractional exponents. For instance, if I take the number 1/2 and I added it in here for x, well, 2 to the 1/2 power, hopefully you remember from your algebra classes that what that means is the square root of 2. If it was 1/4 or 1/3, let's say, if it was 1/3, that would be 2 to the 1/3 power, which would be cubed root, and so on and so on and so on. So those exist. I want you to be aware of that. Now we have here Up here we had f of x equals a to the x, like 2 to the x and 4 to the x. In the second slide, we're going to propose a to the negative x. So you can pause the video if you like and try to determine what the graph of y equals 2 to the x, 2 to the negative x, and y equals 4 to the negative x. Let's consider those two graphs, see if you can figure out what those look like compared to these. I encourage you to pause the video and then resume it once you've come up with an idea. We will move forward here. This is what we should come up with. Just like I did in slide 1, I made a table of values. I actually chose the same values. But because the exponent is negative, it reverses the behavior. The thing that the 2 used to produce in this graph, 2 produced a 4, now that's going to be produced by the negative 2, because we're changing the sign of the x value before we take 2 to that power. So what this does is, instead of the graph having an asymptote on the left side, crossing 0, 1, and then growing on the right side, it's going to be a reflection of this graph across the y-axis. So it's going to get larger as I go to the left, because when I go to the left, that means the x values are negative. A negative negative becomes positive, so 2 to a positive power grows. And just like before, we have in blue here, I have the 2 to the negative x, and in green, I have the graph of 4 to the negative x. So because 4 is a bigger number, it's going to grow faster once the exponents are positive. But when the exponents are negative, and I know this is the positive x's, but in this function, that produces a negative exponent, the green graph will actually get smaller, for the same reason that these graphs get smaller when we go to the left. It's just reversed now because the exponent has been changed. Here's some properties that you're going to want to become very familiar with. You've seen these before, but this is a little bit of a review. These are properties of exponents, and so what I'll do here is give you a demonstration of each of these. A to the x times a to the y is equal to a to the x plus y. Now notice these are a and a. So for example, if I take 2 to the third power times 2 to the fourth power, according to this rule, that should equal 2 to the 3 plus 4, which is 2 to the 7th. And then let's see what 2 to the 7th power is. We'll bring up our calculator here. Okay, so if I just type in 2 to the power of 7, you can see that that is 128. Now I'll do it differently. Let me take 2 to the third, that's 8. 2 times 2 times 2. And I'm going to multiply that times 2 to the fourth, which is 16. I also get 128. So this verifies that that rule works. Here we have a division. So I'll do the same thing. I'm going to take 2 to the, oops, let's get my pen working here. Let's take 2 to the 6th, for instance, divided by 2 to the 4th. According to this property, that should equal 2 to the 6 minus 4, which is 2. 2 squared is 4. So the first thing we'll do, well, let's verify that. In the numerator, we're going to figure out what's 2 to the 6th. That's 64. In the denominator, we have 2 to the 4th. That's 16. So what is 64 divided by 16? It's 4. So that's a demonstration that that actually works. A to the negative x, we've already introduced this one. We'll mention it here. 2 to the negative third power, for instance, is 1 over 2 to the positive third, which is 1/8. 2 times 2 times 2 is 8. And 1/8 is approximately 0.125. Where's my pen? There we go. So we'll demonstrate this in the calculator as well. I'll type in 2 to the power of negative 3. I get 0.125. That's the same thing as 1 divided by 8. Anything to the 0 power is 1. We can check that out here as well. 2 to the 0, 5 to the 0, 0.256, whatever that may be. Oop, I forgot the decimal. Wanted to put a decimal there. To the power of 0 is also 1. Anything is going to give you 1. Okay, let's try pi to the power of 0. That's an irrational number. It's 1 also. The only number this ain't going to work for is 0 raised to the 0 power. Okay, we can't have that. So any number raised to the 0 power is 1. So we'll just go ahead and verify that we have that. Okay, I've shown you that. Here we have a product raised to a power. So for instance, 2 times 3. Actually, let me change this 2 here to a 4. 4 times 3 to the second power, say for instance, according to this rule, that's going to be 4 squared times 3 squared, which is 16 times 9, which is 144. Well, here, 4 times 3 is 12, and 12 squared is also 144. So that's a demonstration of that rule. Up here, we'll have 2 to the third power raised to the fourth power. According to this rule, this is going to be 2 to the 3 times 4, which is 12. And if I type 2 to the 12th power into my calculator, I get 4,096. Well, that's the same thing as if I started by saying, what's 2 to the third power? Well, that's 8. Now type into your calculator 8 to the power of 4. You also get 4,096. So it demonstrates that that works. We have our last 2 here. This one's going to be, let's say, 4/3 squared, just to make this one up. According to this rule, that's going to be 4 squared divided by 3 squared, which is going to be 16 divided by 9, which is the approximate decimal 1.7 repeating. Well, if I just take 4/3 and type it into my calculator in a parentheses and ask it to square it, you'll see that you get right to there. So this rule works. And finally, the last one, if I have something like, say, the absolute value of 3 squared, this rule says that that will just equal 3 squared. Even if a is negative, we're going to end up squaring it anyways. It's going to become positive. So those are our properties of exponents. I'm going to go ahead and terminate this first video, continue with a second.